Position. The position tolerance is used to control the location of a feature, let's say a hole. And the way I do this is by pointing at the feature I want to control. So in this case, I want to control the center line of the hole. I point at the dimension line and I say the position tolerance is 0.1 with respect to some datum. Then I have to define my datum. Here's datum A. This means I want to control this distance here. So I have to define this distance using a theoretical dimension. Let's say it is 10 millimeters. This means I have my tolerance zone, which are two lines with a distance between them of 0.1. And the ideal line in the middle between these two lines lies with a distance of 10 millimeters from A. Now, I can go ahead and also define another datum B here. So in this case, this is that other surface. And I say also to B, I have also here to point with a theoretical dimension, an ideal distance, which is, in this case, also 10. This means I have a tolerance zone which looks like that. Now, I can put the diameter sign here, which means I have to modify my tolerance zone, which was this square here. I have to modify it to be a circle. So now I have my tolerance zone, which is just a circle with a diameter of 0.1, and the center line of the hole it has to lie inside. Now I can continue further and say that this surface here is datum C, and I can also put it here as datum C. This means if I look from that view here, it looks like that, and here is the hole. This means that the center line of the hole, which in reality might look like that, is perpendicular to C within a diameter of 0.1. And you see, location tolerances already control the form and orientation for the elements in addition to their location. Now you can see the benefits of using a position tolerance over a plus-minus size tolerance. The first benefit you see already is by using datum C, you control the perpendicularity of the hole. Another huge benefit is that you can use the diameter modifier. But why is it better? Let's see. You could have said 10 plus minus 0.05, and this means also a distance of 0.1 from B. If you look at the tolerance zone without using the diameter sign, it'll look like this. And your measurements will lie like that. All these points are not accepted, but once you use the diameter modifier, you actually increase the tolerance zone without any negative effect on the function. You transformed your tolerance zone to a circle with a diameter of 0.141, which looks like that. Usually for your function, what matters for a hole is the radial distance of the deviation from the ideal center line. If you had to look at the point that lies here or there, you accepted them in the first tolerance, which was 0.1 using normal plus and minus tolerances. Although they actually have a radial distance to the center of the hole of 0.141. So why did you refuse this point, although it lies on the same distance from the center? The effect on the function is the same, but in this case you had to refuse it because it lies outside your tolerance. But using the diameter sign, you allowed all this extra tolerance zone without negatively affecting the function. This is about 57% more tolerance zone, so your part is actually cheaper while satisfying the same function, just by changing the definition of the tolerance from plus-minus system that was so limited, you had to refuse points that could have been okay. You have much less scrap, and you save money. I hope you're still not thinking about using plus-minus tolerances to tolerate the position. A third benefit of the position tolerance over using size dimensions to control the location is due to using the datums. We will see later that the definition of a feature as a datum makes it being considered in the measurement in a way very similar to the function of this feature in the assembly. If you look at the real surface, A, it would look like that. The problem with using plus and minus tolerances here is that your distance to A here is 10. But if you measure here, you get another measurement result. So the distance to A is not really one value, but depends on where you measure. But GD&T solves this problem in a brilliant way. Datum A, to which the measurement is done, is not the real feature, is not the real surface, but it is a rebuild of the surface as it will matter for the function and the assembly. By using A as that datum, the measurement technician will push an ideal surface towards the part, and datum surface A is the real surface. So, you simulate the assembly of the part during the measurement, and measure only what is relevant for the function. How brilliant is that? To summarize, we saw that position saves cost by allowing more tolerance zone without negatively affecting the function. We saw that it simulates the function and assembly of the part during the measurement rather than just giving a random result. Also, using position means that you control the form of the element and the orientation, because the tolerance zone has to be parallel to the datum. All of these advantages for using GD&T over just a size dimension to tolerate location makes it extremely important to consider using position whenever there is a chance.